Hey everybody, I'm going to do this theorem over again because after I did it, I realized there was a much better way to do this proof. The best way to do this proof is by contradiction. And here's the theorem. It's an alternate characterization of limit point of a non-empty set S of real numbers. And I guess I'm going to redo my writing here also. A non-empty set S of real numbers. And here's the alternate characterization. The same one I put up before. A real number P is a limit point of a non-empty set of real numbers S if and only if, for all epsilon greater than 0, the interval P minus epsilon, P plus epsilon contains infinitely many points of S. Same exact statement of the theorem that we proved just a little while ago, like maybe a day or two ago. But it hit me that the way to do this is by contradiction. So obviously when I did the proof the other day and did it directly, I forgot to bring my brains with me and I apologize. So let me write out the first step of the proof. And one thing hasn't changed. Being the brave, courageous, and bold man that I am, I'm going to do the easy part first. Okay. So here I am hitting the chicken switch. I do the easy way first. And we assume that S is a non-empty set of real numbers. And the part that we're going to prove first is, for each epsilon greater than 0, the interval P minus epsilon, P plus epsilon, contains infinitely many points of S. This hypothesis, the fact that this interval contains infinitely many points of S for all epsilon, implies that P is a limit point of S. So we let the hypothesis be given. So this is what we assume. For each epsilon greater than 0, the interval P minus epsilon, P plus epsilon, contains infinitely many points of S. So if this interval contains infinitely many points of S, then all of the points in this interval, except for P itself, all of the points of S, or all of the elements of S that are in this interval, other than perhaps P, I'm still not saying this very well, I apologize. There are infinitely many elements of S in this interval. So we can pick one. Actually, we can pick infinitely many of elements of S in this interval that aren't equal to P. So there exists an element of S, and we'll say actually infinitely many. But there exists an element of S in the interval P minus epsilon, P plus epsilon, other than P itself. So there are infinitely many elements of S in this interval, and at most only one of those elements of S is equal to P. So pick an element of S other than P that's in this interval. So this means that the interval P minus epsilon, P plus epsilon contains an element of S other than P itself, and that by definition means that P is a limit point of S. So that's the end of the first half of the proof. I guess I better erase this. But yeah, by our hypothesis, there are infinitely many elements of S in this interval. At most, only one of those elements of S can be equal to P. So there are infinitely many elements of S in this interval other than P. So pick one. And this means that the interval P minus epsilon, P plus epsilon contains an element of S other than P itself. And that by definition of limit point means that P is a limit point of S. Now we'll do the converse. Okay, here we do the converse. If P is a limit point of S, then for each epsilon, oh my goodness. For each epsilon greater than 0, the interval P minus epsilon, P plus epsilon contains infinitely many points of S. So our hypothesis, P is a limit point of S. Our conclusion, for each epsilon greater than 0, the interval P minus epsilon, P plus epsilon contains infinitely many points of S. And we're going to do this by contradiction. So we assume our hypothesis. We suppose that P is a limit point of S. And then we inform our readers that we're going to be doing this part of the proof by contradiction. So suppose, for the sake of deriving a contradiction, that the conclusion is false. In other words, there exists an epsilon greater than 0 such that the interval p minus epsilon, p plus epsilon contains only finitely many points of S. And we'll look at case 1. Yeah, I guess the negation of this interval contains infinitely many points of S is that this interval contains only finitely many points of S, or perhaps none at all. So we'll look at this case first. And I'm going to have to modify this a little bit because this interval is going to contain P, isn't it? So for the sake of deriving a contradiction, there exists an epsilon greater than 0, such that this interval does not contain infinitely many points of S. So either it contains finitely many points of S other than P, or perhaps no points of S other than P. So we'll consider the case where it contains no points of S other than P first of all. Now, if this is the case, if the interval P minus epsilon, P plus epsilon contains no points of S other than P, then by the definition of limit point, P is not a limit point. which contradicts our hypothesis. Remember the definition of limit point? P is a limit point of a set of real numbers S if every interval of the form P minus epsilon, P plus epsilon contains a point of S other than P itself. So if the interval P minus epsilon, P plus epsilon contains no points of S other than P, then by definition of limit point, P is not a limit point of S, and that contradicts our hypothesis. So now we come to case 2. So here's the other case. The interval P minus epsilon, P plus epsilon contains only finitely many points, n of them. Finitely many points of S other than P itself. And I'll clear up some board space and we'll see why that's a problem. So we're considering case 2, the interval P minus epsilon, P plus epsilon contains only finitely many points, S1, S2, dot, 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 S sub n. Finitely many points of S other than P itself. So for I equal 1 to n, we let delta sub I be the absolute value of S sub I minus P. Now, what is this thing actually? Absolute value of S sub I minus P. This is the distance from S sub I to P. And now, let's see, how many of these do we have? We have n of them. Finitely many. And there's this very obvious fact that we keep beating to death because it just seems like it's not a natural thing to think of when we need it the most. But delta sub I, there are n of these, delta sub 1, delta sub 2, delta sub n. We have a non-empty set of finitely many real numbers, delta 1, delta 2, dot, 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 delta n, a non-empty set of finitely many real numbers. And what is always the case? There has to be a largest value, and there has to be a smallest value. So let's look at the smallest value. Yeah, this interval contains no point of S other than perhaps P itself. If this interval did contain an element of S other than P itself, then the distance from that point to P would be less than delta over 2, which would mean that delta is not the smallest of these numbers. See, any point of S other than P that's in this interval is also in this interval. And any point in this interval is going to be less than delta over 2 units from P. But delta is the smallest of the distances from the points of S in this interval, the points of S in this interval to P. So any point of S that's in this interval has to be in this interval, and its distance would be smaller than delta. That can't happen. So this interval, P minus delta over 2, P plus delta over 2, contains no point of S other than perhaps P itself. We've chosen delta so that actually none of the points in this interval are going to be within delta units of P. So we have this interval, P minus delta over 2, P plus delta over 2, containing no point of S other than perhaps P itself. What's the problem? Well, maybe if we renamed delta over 2 as something else, we'd see what the problem is. Whoops. Never mind. Just by the very definition of limit point, if we're letting this function as our delta, we have an open interval centered at P that contains no point of S other than perhaps P itself. This implies that P is not a limit point of S, contrary to our hypothesis. So we assumed that there's an epsilon greater than 0 such that P minus epsilon, P plus epsilon contains only finitely points of S, finitely many points of S, yields a contradiction. The assumption has to be false. If we assume this interval contains only finitely many points of S, that we get a contradiction. The assumption must be false. Hence, tell you what, for all epsilon greater than 0, okay, there we go. Proof done.